All right, so first off, let's start talking about bond energies. And bond energy is defined as the energy required to break 1 mole of bonds. So let's take a look at this. So this is something like Cl2 as a gas being broken up into 2 Cls. And so you're breaking that Cl-Cl gas. And this requires energy. So this is 243 kilojoules. So it takes 243 kilojoules to break apart 1 mole of Cl2. Let's take a look at another one, HCl. That breaks up into H and Cl. And so if we take a look at the delta H of this, we see that it's higher, 431 kilojoules. And so since this one is higher, it takes more energy to break that bond. That means that this HCl bond is stronger than a Cl-Cl bond. And so one important caveat to this is all in the gas phase. When you start talking about solutions and stuff and solvents, things get a little bit more complicated. So some bonds are stronger than others, and you can see that these bond energies are positive. So it takes energy to break a bond, but that also means that when you create a bond, that actually releases energy. So a lot of times people think breaking bonds releases energy. No, that's not true. It's the creation of stable bonds that releases energies. Let's take another look at another example. So N2 as a gas being broken up into 2 N's as a gas. And so if we look at the delta H of this bond, it's 946 kilojoules. And so we can see that's much higher than the other ones. And so kind of think about why is it higher? Well, if you draw the Lewis structure of N2, what you'd see it's a triple bond. And so when we're talking about this bond energy, we're talking about breaking all 3 of those bonds, all 3 of them. And so triple bonds here are obviously going to be higher in energy to break, and so they're stronger bonds. Kind of makes sense, right? A triple bond is stronger than a single or a double. The picture in real life is actually a bit more complicated, and it's because actual bond strengths depend on the whole molecule. Bonds and molecules are all just kind of one big thing. They're not individual things. They're always interacting. And we'll see this more later on when we get into molecular orbital theory. But for now, we're just going to say that the actual bond strengths depend on the whole molecule. So for example, if you have this H3C and then the CH bond, so this is the bond that we're looking at right here, this CH bond, this delta H is 438 kilojoules. Whereas if we take a look at this same bond, right, still this CH bond, but now this carbon is bound to 3 chlorines instead of 3 hydrogens, its delta H is now 401 kilojoules. So you can tell that the other components of the molecule affect the bond strength. And so what do we do to resolve this? Well, we kind of just be lazy and we just use the average. And remember, triple is stronger than a double, and a double bond is stronger than a single bond. Kind of makes sense. And so we can look up these tables that have these average bond energies. So there's the one from your book, OpenStax, and you can tell there's all kinds of different bonds and their strengths. You know, here we've got nitrogen single bond, double bond, triple bond. You can tell as we move up in more bonds, we get stronger and stronger. And so we can use these bond strength to estimate the enthalpy of reactions. And so the equation goes delta H of this reaction is going to be equal to the sum of the delta H's of the bonds broken minus the sum of the delta H's for your bonds formed. And this table is in the delta H's, right? So you're just going to pull information from this table to get an estimate of the enthalpy of reaction. It's not going to be perfect because there are some assumptions and some differences in real life, but it gives a pretty good estimate. So let's take a look at an example. CH4 plus 2O2 going to CO2 plus 2H2O. So the combustion of methane. Let's take a look at this. You have to think about what your Lewis structures look like. So CH4, if you were to draw this Lewis structure, it would look like that. And so we're going to break all of these bonds. So we're going to break 4 CH bonds. And then we look at this O2. If we were to think about the Lewis structure there, I'm not going to include all the lone pairs and whatnot, but it's a double bond. And so we're going to break 2 of these double bonds because we have 2 O2s. Cool. So let's take a look at what bonds we're going to form. If we think about the Lewis structure here of CO2, again, I'm not going to include all the lone pairs, but it's 2 C double bonded O bonds. So we're going to form 2 C double O bonds. And then if we think about water, again, I'm not going to draw in the lone pairs, but each water has 2 OH bonds, and then we have 2 waters, so that's a total of 4 OH bonds. Cool. So the next step is to look them up in this table. So let's start off with the CH bond. So we look in our table and we see CH is right there. And since we're breaking those bonds, we're going to leave it as a positive. So we're just going to multiply this number by 4. Next up, we have O2 bonds, right? A double bonded O that's right here. So we're going to multiply this by 2. Next up, we've got CO bonds. We've got 2 of them. We look them up in the table. It's right here. So we're going to multiply that by 2. And then we have 4 OH bonds. So we find our OH bonds. It's right over here. And so we're going to multiply that by 4. And so I'm just going to rewrite this here. On this side, we've got 4 times 415. And then we've got 2 times 498. And then on this other side, we've got 2 times 741. And then 4 times 600 or 464. Cool. And so the other thing you have to realize, it is bonds broken minus bonds formed. So we're going to sum this side, we're going to sum this side, and then we're going to subtract one another, subtract these 2 values. And then this is going to be equal to our delta H of reaction. And so if you go ahead and do the math, you get the delta H of reaction to be equal to negative 682 kilojoules. So we have an exothermic reaction. That makes sense because we're doing combustion. Think about combustion. It's hot, it's exothermic. And so remember, the energy is released when bonds are formed. So it takes energy to break these bonds, but then you release energy when you form these bonds. And since these bonds on the right are more stable than the bonds on the left, the net effect is a release of energy or an exothermic reaction. So again, just to re-clarify that point, because a lot of people, it's a big misunderstanding in science. It takes energy to break bonds. Forming bonds is what releases energy. What's going on here is we're going from an unstable state to a more stable state, and thus releasing energy.